adenylate cyclase does is it converts ATP into cyclic AMP. This is a very important step. Okay.
And the gamma alpha subunit
Are not involved.
They haven't bound to the adenylate. What bound to the?
This is what interacts with it.
Oh, it just interacts. It doesn't bind.
Yeah, I don't think there's a direct binding here.
Okay.
The point is that there's some sort of interaction.
Okay.
Okay. What that does is it increases the activity, right? Gas.
Yeah.
Increases the activity of adenylate cyclase, which makes us get more cyclic AMP, because adenylate cyclase catalyzes ATP into cyclic AMP. Okay. What our cyclic AMP will do, I'm just going to draw it like this. That's an arrow.
That's an excellent arrow.
Cyclic AMP will bind to a molecule called pKa, right? We had pKb, we have pKa. So what pKa is it's a tetramer with 4 subunits.
Ouch.
2 of them are the same, and 2 of them are the same, but not the same as the other ones.
You're welcome for that, Samantha. I hope that was crystal clear as mud.
We have 2 R subunits, which are called regulatory subunits, right? So they're going to inhibit the activity of pKa. And we have 2 catalytic subunits, ones that actually do work for us.
Okay.
So what cyclic AMP will do, and remember this whole molecule is called pKa. So what cyclic AMP will do is it will bind to the regulatory subunits, change their conformation, and release the catalytic subunits. Therefore, pKa is actually active and can do stuff. Exactly. Right? So in gas, everything gets upregulated, right? We increase the activity of adenylate cyclase, we increase the production of cyclic AMP, we increase the production of pKa. Okay? So that's great, but just like in our muscles, right? If you don't have any way to turn it off, you're just gonna keep like this, right?
Okay, I feel really stupid.
Excellent.
Thank you. So, I guess I'm missing where the G alpha subunit comes from in relation to his alpha 1, alpha 2.
This is okay, so this is G alpha S subunit.
Okay. So it's one of the beta.
Yes, so this receptor would be called a beta 1 or a beta 2 receptor. So this is in reference to the receptors. This is in reference to the molecule involved.
Okay.
Okay?
But the G alpha S, I think that's where she's getting confused. So those are receptors, which would be from the ligand area, or no, yeah.
I don't know if I understand what you just said.
You said
It's
G alpha
it's
S.
Alpha Q, it's alpha.
G alpha S. Yeah, so this is G alpha.
There you go.
One
All
of
of
these.
those. Okay.
G alpha Q, G alpha I.
And then the alpha 1, alpha 2, and beta are the categories of receptors.
Correct.
Gotcha.
Yeah, so we repeat S because there's a beta 1, there's a beta 2, there's a beta 3, but there's not like another S. There's
Okay.
just S.
It's just the same S.
Yeah, it's the same S.
Same
Okay.
S hole.
The same S hole, yes. So we need to turn this off, right? Because if there's no turn off function, we're just going to keep making more and more cyclic AMP. We're going to keep upregulating pKa. Our turn off is a timed and is time based. It is not sensitive to pH. It's not sensitive to other molecules. It is time based only. What will happen is this GTP will get turned back into GDP.
Okay.
Okay.
You run out of nitrogen.
Yeah, exactly. You run out of, nitric oxide. So what that does, we turn GTP into GDP, stops our car, inactivates it.
Okay.
I don't know how these get rebound, but that does not matter for what we need to know. They have to
Yes,
get
you.
rebound. Yeah, some guy comes by with glue or something. I don't know. So,
Little tiny man.
yeah, a little tiny man. So GTP gets turned into GDP, stops the upregulation of adenylate cyclase, stops the production of cyclic AMP, stops this conformational change, and therefore stops the production of pKa, active pKa.
So I know it's a conformation change and it releases the catalyst. do they just rebind, or is it?
I don't know.
Okay, whatever. It just
Yeah, I don't know.
it just reforms. So, yeah. Okay.
So this is